This is section 3.3. This example just should have been in the last video on part 2, but the last part 2 video ran a little bit longer than I thought it would, so I'm just going to include it in a separate video. To find the absolute extrema, it's very similar to find the relative extrema. We're still going to be using the first derivative test, but for absolute extrema, we're going to be given a specified interval. So there's a slightly different process towards the end of the problem as to figure out what's the maximum and what's the minimum. So the problem starts off the same. I still have to find my critical points. So I'm still going to be using the first derivative test. So to find the critical points, I need to find out the derivative. This derivative requires the use of the product rule, and when I get to this one, I'm going to be using the chain rule. So this derivative is going to be x squared, and then it's going to be e to the negative 2x. Chain rule on negative 2x is negative 2, plus keep e to the negative 2x the same, and now the derivative of x squared is 2x. So cleaning this up, this is going to be negative 2x squared e to the negative 2x plus 2x e to the negative 2x. I'm going to set this equal to 0. Now I have a common term of e to the negative 2x I'm going to factor out. And what I have left over is negative 2x squared plus 2x. Set this equal to 0. Now I can go ahead and solve this. This is going to be e to the negative 2x is equal to 0. And then negative 2x squared plus 2x is equal to 0. I have a common term that I could factor out, which is negative 2x parentheses. This would give me x minus 1 is equal to 0. If I factor out a negative number, that switches the sign from positive to negative, and I can go ahead and solve this. 2x is equal to 0, x minus 1 is equal to 0. So 0 is a critical point, and x is equal to 1 is a critical point. Now, as far as this over here that I factored out, e to the negative 2x is exponential decay. It looks like that. It's never going to cross, it's never going to hit the x-axis, so this does not have a solution, so I don't have to worry about it. It's not going to give me a critical point, so this factors out, and it's never equal to 0, so it doesn't give me a critical point. Just these two values are. Now I have to conclude with the sign analysis for the first derivative test. I'm looking for specific sign changes in the first derivative. So I'll put these numbers on a sign chart. It's going to be 0, it's going to be 1. And I'm plugging in numbers in between 0 and 1, before 0, after 1, into the factored derivative. So I can plug in, let's say, f prime of negative 1, f prime of a half, and f prime of, let's say, 2. Alright. If I plug in negative 1 into this factored derivative, this is going to be a positive number times a negative number. So positive times negative is negative. If I plug in a half, this is still going to be a negative number. This is going to be a negative number, so two negative numbers give me a positive. When I plug in 2, this is going to be a negative number times a positive number, so that's going to be a negative. So based on this negative to positive, this is going to be a relative. If I have a negative to positive, it's going to be a minimum. And based on the positive to negative, this is going to be relative max. But this is how it differs because it's an absolute extrema and it's given on an interval. I have to see if these two are in fact the lowest and the highest endpoint compared to the overall interval. So for absolute, you have to compare not only the relative extrema, but then you also have to compare to see if the endpoints are the smallest and the biggest values. So I'm going to have to plug in the critical points into the function. So it's going to be f of 0, it's going to be f of 1, and I also have to plug in now the endpoints. So f of 3 and f of negative 0.4. So these values that I'm also checking are going to be the endpoints. So because it's on a closed interval, I have to look to see if these endpoints are either a maximum or a minimum. And the way I plug these values in, I'm going to have to use a graphing calculator to get these answers. So when I plug in negative 0.4, when I plug it into the calculator, I end up with 0.356. When I plug in 0 into the function, I end up with 0. And I'm plugging it into the f of x. I'm plugging it into this. When I plug in 1 into the function, I end up with 0.135. And when I plugged in 3, I ended up with 0.022. So from these four, I have to decide which is the biggest value and which is the smallest value. And I can see that the biggest value is at this one over here, and I can see that the smallest value is at this one over here. So I can say that the absolute maximum occurred at the endpoint. So it's going to be negative 0.4 comma 0.356, and the absolute minimum happened to occur at one of the critical points, which was at 0, 0. And here's a graph of this function to kind of illustrate that the maximum occurred over here at negative 0.4, and at the lowest point, the minimum occurred over here at 0. And even though this is a relative maximum, it's not the biggest maximum, and that's what kind of absolute extreme to look for, is like the highest point on the graph in the specified interval. So I'm looking at the highest point on this interval, which happens to be at the endpoint, and the lowest happens to be at the relative minimum. And that's it for this one video, and I can discuss further in class tomorrow.